In part 3 of this series of presentations, we have shown how the classical Dirac equation can be derived from the Einstein-Hilbert action. Thereby, we partially followed Dirac's path and used some of his assumptions, especially the assumption of a flat spacetime. In contrast to Dirac, however, we did not factorize the Klein-Gordon equation, but derived this equation directly from the Einstein-Hilbert action, thereby coming to a much more general, if not to say, a metric form. We have also demonstrated that only a scalar part of the Einstein-Hilbert action is of need in order to derive the Dirac equation, classical and metrical, while the tensor part was assumed to be small. In this presentation, we now want to generalize our approach. A theory of everything, for which we are aiming here, should not only contain Einstein's general theory of relativity, but also all major quantum equations, and it should also explain the appearance of what we describe as matter. In previous presentations in this series, we have already shown how we can extract the Klein-Gordon equation from the Einstein theory of general relativity, part 2, and that matter does not need to be postulated, part 1. In part 3 of this series, we concentrated on the metric derivation of the Dirac equation as one of the most important relativistic quantum equations. The Dirac equation is a matrix equation which contains the Dirac gamma matrices and the beta matrix. Even though on this slide we only give those matrices for the case of four-dimensional spacetimes, in part 3 we have derived a general metric Dirac equation for n dimensions directly out of the Einstein-Hilbert action. Thereby we had assumed that the metric variation, which is the essential part of Hilbert's calculus, was dominated by its scalar, volumetric part. Here now we will try to generalize this concept. Our starting point is the so-called Einstein-Hilbert action, a variational integral based on a Hamilton extremal principle. Already in 1915, it was the great German mathematician David Hilbert who derived Einstein's field equations from such a fundamental minimum principle. What Hilbert apparently did not see was that his formula in fact contained much more than just the Einstein field equations, but that he had also found the fundament for quantum theory. In this presentation, we will now show what Hilbert had missed, or, taking Hilbert's genius, simply not considered important enough to be mentioned at all. It should also be mentioned that the Dirac equation was not postulated before 1928, and so Hilbert, who had published his world formula 13 years earlier, had no chance in seeing the need to extract something as weird as Dirac's matrix equation with its even weirder spinor solutions. As we have already shown in part 1 of this series that we do not need the matter term Lm nor a cosmological constant to obtain matter, we set both lambda and Lm equal to 0 and just proceed with the curvature of spacetime, known as the Ricci scalar, as the kernel within our variation. Now, by following Hilbert's classical derivation, we obtain the so-called vacuum Einstein field equations. Things change, however, in a rather interesting manner when introducing a slightly adapted metric tensor with a scaling factor as shown here. The meaning and potential origin of the index I will be discussed later in this presentation. So far, we have to admit that we have no inkling where such a Liszt character of the scaling function could come from. Hilbert's variation now yields a much more complex kernel. Thereby, we use such a peculiar form because it allows us to spot the direct appearance of classical quantum equations in the case of the most commonly used metrics. For more information, the reader is referred to the books given at the end of this presentation or in the video description underneath the video. Please note that the integrational kernel can dramatically be simplified by demanding the scaling function to fulfill a special condition. We treated this path in our second part of the series, where we derived the metric, which is to say the generally quantum relativistic Klein-Gordon equation. From here now, we could simply repeat our evaluation with respect to the Klein-Gordon equation, see our corresponding previous presentation on this matter in part 2, and then apply Dirac's strategy to factorize the Klein-Gordon equation. This, however, will only lead us to the classical Dirac form and not to a metric generalized one. Thus, we will avoid the condition for f and proceed as follows. At first, we split up the variated contravariant metric tensor into its scaling and its tensor part as shown here. And then we result in two equations, a scalar and a tensor one. At first, we want to repeat the derivation of the simple, which is to say scalar-based Dirac equation. Thus, we ignore the tensor equation, for example by simply assuming that the variation of the metric tensor gives 0. Then we intend to fulfill the scalar, which is to say the first equation, by demanding the kernel of the integral to be equal to 0. This gives us the following partial differential equation, and by inserting the simplest possible setting for the scaling function f, we get things to clear up a little bit. In the next step, we add in the Dirac starting point, where we assumed that a. the spacetime can be assumed Ricci flat, and thus r equals 0, and b. the Laplace operator has an eigenvalue m squared. Now, by using the connection between the Dirac gamma matrices and the metric tensor, we can directly derive the metric generalized Dirac equation as shown here. As one of the factors in the last line suffices to fulfill the whole equation, we easily recognize the Dirac equation in its classical form. We realize that, in our metric generally relativistic theory, the metric scaling function, which is nothing else but a volume factor, is just equivalent to the quantum theoretical wave function. Just as with the classical Dirac theory, however, the functions Fe have to be eigenfunctions to the Laplace operator, which is to say, they have to fulfill the Klein-Gordon equation too. In order to assure this, only a limited number of solutions to the matrix equation connecting the metric tensor and the gamma matrices is allowed. Now we intend to further generalize our metric Dirac equation, which is a matrix equation, but still only solves the scalar part of the Einstein-Hilbert action, to a more truly quantum gravity Dirac equation, and go back to slide 7 and the general outcome of the Hilbert calculus in the case of the scalar scaled metric as being used here. But we shall also mention at this point that our simple scaling we have used so far, quite successfully by the way, when considering the fact that we have derived the Einstein field equations, the Klein-Gordon, the Dirac and the Schrödinger equation just all out of one formula, namely the Einstein-Hilbert action, is really only the most dramatic simplification of a much more general adaptation of the metric tensor. For completeness, we show this general form here as well, in the blue ellipse, and will discuss it in later presentations. For here and now, however, we are not going to apply it, because the simple version already leads to a variational kernel which is cumbersome enough. Treating it like the classical Einstein-Hilbert action and demanding the whole integral to vanish gives us the quantum Einstein field equations. Thereby, the red ellipse shows us that the classical Einstein field equations are a part of the new set, making out the metric or G-related terms, while the rest is connected with the scaling function and thus the local volume of the spacetime under consideration. Just to give an example, we solved the complete tensor equation for a very simple metric case in 4 dimensions with the following tensor. We realized that r has become an angle, while t took over the position of a radius, where we have assumed the object to just live with a fixed time shell t equals rho in a spatial part of our metric. Here, things are getting very interesting when we investigate the shell's radius rho. Comparing the solutions for f with the classical particle at rest solution, we realized that the mass of the object, here expressed via the Schwarzschild radius, makes the object smaller with increasing mass. Lp denotes the Planck length and thus a very fundamental natural constant, which may be seen as the smallest possible distance one could resolve in our universe. The interesting thing here, the shell radius of the object decreases with the mass increasing. Thus, the object becomes smaller when getting heavier. Here we have a chance to potentially fill the inner part of a black hole with massive objects without the need of a singularity. Taking the full kernel of our scaled Einstein-Hilbert action and assuming the gravity part to be small against the volume, we end up with a scalar differential equation. It already was shown in our earlier presentations that this equation simplifies to the standard quantum equations when we assume certain metrics. The characteristics of such metrics is given on slide 9 of this presentation, and we see that these exactly are the typical and often used metrics like the Minkowski metric in Cartesian, spherical or cylindrical coordinates. Here now, however, we leave the metric general. Incorporation of the functional wrapper F of f property, we obtain a partial differential equation on f. Demanding certain conditions for the wrapper function F, and also demanding the first operator of our scalar quantum gravity equation to give eigenvalues m squared and operator eigenfunctions v properties, we simply take from the character of the classical quantum equations as masses and potentials, which we can easily extract from our quantum gravity equation via the metric properties on slide 9, we, once again, obtain the starting conditions for the derivation of the Dirac equation. In order to see this, simply compare our equation given here in the last line with the equation on slide 13. The only difference is the appearance of potentials v. For the case of vanishing Ricci scalar r equals 0, and by simply following the derivations laid out in this presentation between slides 13 and 18, see also our presentation part 3 of this series, we obtain the Dirac equation again. The only difference is the much more general character of the gravity Klein-Gordon eigenequation we resulted in on slide 25, the first equation on top. This has quite some consequences on the Dirac gamma matrices in general metrics. In the case of non-vanishing Ricci scalar, we see that we ended up, see the last line of this slide, with an equation where the function appears in third order. This is quite interesting because particle physicists are looking for such an equation in order to explain the so-called three-generation problem of elementary particles. The fact that such an equation comes directly out of the Einstein-Hilbert action for a scaled metric sure is worth some further investigations. We note that with the approach used here, we should discuss the following issues. The direct application of the Einstein-Hilbert action does not give us the perfect Laplace operator for all metrics, see the complex operator on slide 25. And there is no separate equation, which is to say the equation we have for capital F of f, even though already clearly mirroring the classical quantum equations, is only a part of the classical Einstein field equations. we try to solve the problem via an additional variation. This time, the variation is with respect to the function f, and we apply the so-called functional derivative, for which we refer to the standard textbooks in theoretical physics. Here on this slide, we assume to have performed the f variation after the standard Hilbert variation under the assumption of weak gravity. As we see in the red ellipse, this time we obtain a perfect Laplace operator. It should explicitly be pointed out that we can obtain the same result when applying the f nudging, which is to say the functional derivation of the Einstein-Hilbert action before the usual Hilbert variation with respect to the metric tensor. Again, we obtain the perfect starting point for the derivation of a Dirac equation, with the recipe being applied on slides 13 to 18. For here and now, where our intention was the derivation of the gravity or quantum gravity Dirac equation, we can now sum up our result. A. We have derived a Dirac equation directly out of the Einstein-Hilbert action integral, and thus consider it a quantum gravity Dirac equation. B. We have found two options. One, where we can obtain the classical Laplace operator starting point directly from the Einstein-Hilbert action via a functional derivative with respect to the scaling factor f before or after the Hilbert variation, and another one where we do not need such an additional variation, but only the classical Hilbert one. In the latter case, we do not obtain perfect Laplace operators. C. The classical Dirac equation can be obtained from this latter result in the case of vanishing Ricci scalar and certain metrics. The first option gives the classical Dirac equation much more directly also for vanishing Ricci scalars, but automatically shows potentials and inertia in certain metrics. D. Via the option with the direct functional derivatives with respect to f leads to perfect Laplace operators, and thus, in certain constellations regarding the squared nabla terms, see presentation 11 of the series, also to the usual Klein-Gordon equations with potentials, we have no such simplicity when only using the Hilbert variation. With this option, as shown on this slide, still assuming vanishing Ricci scalars, but having general metrics, just being Ricci flat though, we have a much more complex Klein-Gordon-like eigenequation as condition for the generalized Dirac matrices. E. However, for non-vanishing Ricci scalars, we obtain third-order algebraic equations for the wave function, which might help us answering the question about the reason for the three-generation problem in elementary particle physics. It should be pointed out that, apart from the r equals 0 condition and the Laplace eigenvalue condition used here in order to follow the original Dirac approach, there are also other options to metrically derive masses and potentials via additional dimensions. This will give further generalized Dirac equations for curved spacetimes and arbitrary dimensional spacetimes. The interested reader may find more information in the books shown here or other publications of this author. We explicitly want to point out here, however, that we do not consider us the first to have found the connection. In principle, namely, it was all already inside Hilbert's ingenious approach, and he only could not see it because, at the time he wrote down his equation, the fundamental equations of quantum theory were not yet discovered, and his main goal was the derivation of the Einstein field equations, and thus, as Einstein had not bothered about also finding quantum equations inside his general theory of relativity, Hilbert, as a mathematician, obviously saw no need to consider the broader spectrum residing in his approach. These new insights open up a variety of possibilities for the most astounding developments, be it inexhaustible sources of energy, future weaponry, metric artificial intelligence, quantum gravity computing, or completely new, and what is much more important, truly unbiased and most holistic modeling tools for almost all sorts of problems. And how could such developments be realized? The optimum is the global approach aiming for the quantum gravity computer and naturalized AI, which is a Manhattan-sized project. How this disrupts everything and makes the owner the global monopoly to just everything can be extracted from the material presented in this talk. Next smaller step is just the naturalized AI, which still is a small Manhattan project. This too already reaches very far and propels the owner into a global monopolistic and long-time leading position, unless somebody achieves a takeover via a working quantum gravity computer tech. Everything else are service projects.